Hi friends, in this video we're going to see how to design an FIR filter using windowing techniques. Here the software uses Matlab. So for any filter design we need general parameters like passband attenuation, stopband attenuation, passband frequency, stopband frequency, sampling frequency. If it is band pass or band reject, we go with passband limits. Okay. Now the next thing is, as I mentioned, it is a windowing techniques. We have five different windows to design an FIR filter. First one is shown here, a rectangular window, and the rectangular window function is given as omega n equal to 1 for 0 less than n less than n minus 1, 0 otherwise. Similarly, we have other three windows here. I did not show Kaiser window function here as it is a little complex one which is dealing with, it will be dealt with the Bessel function. So here are the remaining three functions. You can look at them carefully and we shall go for the program. Okay friends, now we will go for the programming part. So this is my program for FIR filter design using windowing techniques. First I have given the order of my filter as 20. Then I mentioned my passband frequency and then stopband frequency and sampling frequencies, and I converted the sampling and passband and stopband frequencies to in radians per second, and I have put comments in limits of the frequencies because it may be used for band pass and band reject filters. My first window is rectangular window. I get this using the keyword called boxcar. Similarly, the next will be a barlet window. Barlet window will be for triangular. It is a triangular window. Okay. The next window will put it in a comment. Window equal to, we completed boxcar, barlet, and then is Hamming window. Okay, and I'll copy this because next window is Hamming window. Okay, the last window, fifth window will be a Kaiser window. So these are the built-in functions which we use for directly. You can use it for designing of the windows. Okay. Now after I design my window, I need even to convert my cutoff frequency into radians. It's given by FP by Fs here. Okay, Fs is F. Okay. Next is, now we need to store this into FIR1 window. Okay, we need to store the coefficient. We need the coefficients for this, so I'll store it in the B variable FIR1 n comma omega n comma rs, because I need to go with the window here. FIR1 is the keyword we use here. Okay. B equal to FIR1 n comma omega n comma window. And if I want to go with the high pass or low pass filters, Then I need to place a comment here, so I'll just copy this and instead I'll place a comment here. Okay, so for the next time if I use, I'll use a high or low here. Okay, so 1 second, we'll edit this directly. High. Is that okay? Yeah. Now next I need to get my transfer function. So h comma omega directly transfer function. Already in the last videos we have done this. Freg z b comma, I'm considering directly my, why only I given the coefficient b is, I'm directly considering my a value as 1 okay, so I have completed frequency response. Then I need to plot it directly. Subplot of 2 comma 1 comma 1. Okay, plot omega by pi comma 20 log of, I need absolute value of, I used capital H there, so absolute value of capital H. Okay, the next is labeling. X label enough for normal frequencies, I mean normalized frequencies. Y label for magnitude in dB, I think. Okay, this title is magnitude response. Similarly, I'll copy all this. So that the only change I'll do is, this will be my phase response, and here I'll have angle here, and next is here subplot of 2 comma 1 comma 2. Is that right? Before, after subplot, I need to plot my omega by pi values with respect to angle of capital H. Okay, right. Now if we execute the program for window box car, okay, we'll see if any errors are there. No. So save it. Now if I execute it, I think they might have, yeah, I've got the result here directly. Did not use grid here, so I did not get the lines. So this is my frequency response for low pass filter using rectangular window. Okay, and similarly if I here, if I remove the comment, if I place a comment here, and if I remove the comment here, this will be for high pass filter. Now we'll check the high pass filters. This is the high pass filter response using rectangular window. Now, so similarly, if I open this, low pass and high pass are over, and again if I make this as comment, now I'll change my window. That was a rectangular window, So here I use triangular window now. We'll see how the output changes. I think we have got some. We have got a some error here saying that it's a Bartlett window. It is silent here. Okay, this is the Bartlett window response here we get for low pass filter. Similarly, even I can get the high pass filter as just placing the comment here, removing the comment here, and obtain my high pass filter response. So this is my high pass filter response for Bartlett window. So next is same case for wait for Hamming window. Remove this and place a comment here. Remove this and place a comment over here. Now if I execute this and I'll see the output. Yeah. So this is my pass band here up to 0.6. After that all ripples, stop band ripples. Okay. So whatever change we observe is that the transition between the pass band and stop band will be getting nearer to the ideal response. Okay. That means ideal impulse response. That is a change we observe whenever we change different windows. Now if I see the high pass filter again. So this is the high pass filter one. Right? Like that. You can check for even Hamming window also. So instead of doing that, I'll directly go for Kaiser window here, the last window. Yeah. So this is the Kaiser window here. In that video, you can see the previous response. You have seen that the pass band ended at 0.6, whereas here it ended at 0.45. So the response will be getting nearer to 0 instead of going away from 0. Okay, to obtain the ideal response. Check for high pass here. So this is the high pass case. Okay. So this is how we design the ideal FIR filter using different windowing techniques. Here we used 5 windowing techniques for designing of FIR filter. That's all for this video. Thank you all.